Welcome to PyMOL tutorial number 6, question and answer session. What I realised is that on the second session I'd failed to go through a few of the commands which are kind of important on looking at selecting atoms based on proximity to other atoms. So a lot of today's session will be going through some examples of that. But I also had some questions about opening and saving of files. Now if you're on a Mac or if you're on a Linux, for example, if you have a file that contains many different PDBs, you can open those PDBs simultaneously quite easily, and that would just be by typing something along the lines of your PyMOL command and then star.pdb. If you're on Windows, of course, you can just drag multiple PDBs into your open PyMOL session. So that's quite possible. If you open PyMOL from a window, from a directory in which you've double-clicked on your PDB of interest, and then PyMOL opens up, that means that wherever you save PyMOL, so if you went to then type in save temp.pdb and then whatever the object name is, if you did this, it would then save your PDB in that file location from which you opened up the session of PyMOL. If you open up PyMOL by going to your start menu and typing PyMOL, and then you fetch 3chb, for example, and then say save temp.pdb 3chb, and then it saves this PDB for you based on a command that you've written. Then it saves it to a location that the original PyMOL executable was, and you can find that executable out by typing the command pwd, which is the print working directory. And so this will have saved my my PDB that I've saved via using the commands to the location my documents, basically. Okay, so if ever you're unsure as to where you've saved a PDB based on having written a command rather than going to the file menu and saying export molecule, so if you've written a command to save your PDB, you can use pwd to find out where you are. And if you know some very, very basic Unix commands, pwd, ls and cd, you can also then navigate through your file system to get to directories that are important to you. Okay, so proximity selections. Let's have a quick little recap on this, because I kind of touched on it in previous sessions, but I didn't really go into it with as much detail as I ought to have. So this is the PyMOL selection nomenclature page, which I showed to you in tutorial number 2. What I didn't highlight is that if you come down to this proximity selection, there's a bunch of really, really useful commands here, which if you get your head around exactly what they do and how they go about doing it, you can do some pretty interesting things. I think probably the most important one is maybe this within function and this near to function as well, because this is essentially the same as within, but what you can read here, it excludes one of the selections. So let's have an example of how that works. So for example, say you want to find all residues that are in a binding site around an organic molecule of interest. So let's reinitialize our session. We'll fetch one NQU. We'll change our background color by chain, make our organic molecules black, and then color our atoms atomically or elementally. We can remove our solvent and our inorganics because they're just going to kind of get in the way, and then we'll select our ligand. This is just a little shortcut here to select a ligand. So here we're going to select the organic molecules. We're going to select the very first atom of our selection organic molecules, and then we're going to expand that to the first molecule. So this is just a little shortcut so that I don't have to click on one of these guys. It just means that this way I can select a single organic molecule rather than all 5 of them in this particular example. And so I've called that organic molecule ligA as a selection, and now here I can use this near to function. So here I'm going to make a new selection called close, and that's going to be by residue everything on the polymer that is within 5 angstroms of my ligA organic molecule. So if we do this, and say select. Now I've got basically any residue that has an atom that's within 5 angstroms of ligA. And then I can do some selections on that. For example, I can show sticks for the side chain residues. The initial idea here was to select residues around the binding site, and you can see here that just by using, we'll get rid of that, just by using this pretty simple command here of selecting near to 5, we've only selected those residues within 5 angstroms of our ligand. Let's see if we can do this again. Then this is removing atoms outside of a distance using this gap function. So here's a different example. This time we're going to look at so this is a DNA binding protein here, and maybe you're interested in only looking, and it's a dimer here, which means that obviously we've duplicated any interface. So let's just say that we're only interested in looking at one of our dimers, so we can get rid of that, and we're only interested in looking at atoms that are close to the nucleic acid. So here what we can do is we can say that we want to remove by residue anything that's outside of 15 angstroms of the nucleic acid. So we can hit that, and you can see therefore we remove a whole bunch of our protein. And then we can do the reverse and say that we want to remove all things that are outside of 15 angstroms of our protein, which will then remove any nucleic acid. And that means that now we have this kind of more kind of discrete collection of atoms here, which just saves on complexity. You know, it can reduce the amount of burden or strain to your brain when you're trying to look at these interactions. Some binding site visualizations, and again this is using this near to function again, and you could also use the within function as a proxy for that as well. But let's just have a quick look at this. So this is going to be almost back to that first example. So here we're back to selecting one of our organic molecules of this one, and this is just how to then show a surface by doing essentially the same work as we did in the first example. So we can select those residues within 5, and then we can say, well, I want you to show me that as a surface, and then we can set a transparency so that we can see through it a little bit. That should have a comma. So there we are. That's a very quick and simple way of putting on a quick surface around an organic molecule. And then we've got binding site visualization number 2. Now this is a little bit like I showed you an example, I believe, in tutorial number 3, where we made publication quality images, and that's essentially doing a very, very similar piece of work as this here, but we're using a different way of carving through our surface, and the end result is something that maybe looks a little tidier than this, because this, you can see we get these kind of bits sticking out here and there which are kind of unnecessary, whereas you can use the carving function to try and make things a little bit prettier. So again, we just open up our molecule, make a selection. We'll make a selection called ligA for our organic molecule, a selection called prot for our protein. Let's just see, yeah, we've done that. And then we'll set these carve distances here, where we're going to make a 4.5 angstrom carve around the molecule ligA. And then we can show that surface within 8 angstroms of ligA. And then you can set a few different things like this two-sided lighting. I think I went through this in the previous session. We can set our transparency, orient and zoom in on our ligand, like such. And now you can see that we've kind of, the way that this cutoff works is that we've kind of neatened up this surface that we have around our ligand. It's kind of up to you which one of those two methods that you use, but I think this one is just a little bit nicer. Then we can add a few extra features. So here we can use our proximity selection again. So we're going to select any residues that are within 5 angstroms of our ligA, and then we'll stick our sticks back on like we did last time. There they are. Let's make our surface color white, and then we can make our ligand, make our hydrogen bonds to our protein from our ligand, and we can set them as a nice color. And maybe what we should also do is to hide labels as well, because they kind of get in the way. And there we are again, just another kind of quick and easy way of making a nice looking figure that actually shows some interactions, surface interactions and hydrogen bonding interactions with our protein of interest. So I hope you can see that there's a bit of power here in these proximity selections. So have a read of these and find out how they work and have a bit of a practice, and you'll see that they're actually really quite useful. Okay, so still talking a little bit about proximity selection, but how to use that in different ways. I've also got a question about crystal lattices and how you can tell whether you have amino acid positions in places that are responsible for the crystal lattice interactions rather than for it being responsible for a biological function of some kind. So let's bring in a new PDB. Here we go, and we're gonna name our segment by original PDB or something like this. So here we're just going to name our original segment, make our background white, etc. Remove all of the rubbish that we want. Now, if you want to look at how the crystal is packed, you can use this function called simx. And again, you're making an object called sim, and we're doing it around this particular object and a distance here of 4 angstroms. So here what we're going to do is we're going to show all symmetry mates that are within 4 angstroms of our original object. And there we go. So we can see that these are the crystal lattice packing subunits here. And then what we can do, you can see here that because we've had this sim prefix here, all of our objects from our symmetry mates have this sim prefix. So what we can do is we can use that to give all of these a segment identifier called cris to show that they're crystal lattice interactions, and then we can use the PDB and the cris segment identifiers in order to differentiate between these a little more easily. So then we can colour our crystal guys in white, we can colour our original PDB in black so that we've got some nice contrast between those. As I said, we're interested in crystal packing interactions, and maybe there's a particular loop that you're interested in. So we can use this peptide sequence here to find the loop on our protein of interest. And there it is there. And then we can use some proximity selections here to select residues on the asymmetric unit and residues on the crystal partners here in order to find out how many residues that are in contact with our loop of interest. So for example, we're going to call the loop green, we'll call it a loop section, and then we'll use near to again to find everything within 5 angstroms of our loop, and we'll colour them cyan. And so these are all of our things that are near to us. And then we can do the same thing here, but now not looking at our asymmetric unit, and therefore we'll look at our crystal unit. And that's going to colour in pink anything that's there from a crystal lattice interaction. And then we can zoom in, colour our atoms by their atomic colouring. And then in order to clean up all of this junk here, we can use this gap function with the remove again. And what we can do is just carve away all of those crystal contacts that are outside of 15 angstroms of our loop section, just in order to tidy up our view and make sure that it doesn't seem too complicated. And we can see here now that in our loop section of interest, we probably do have a crystal contact here. We have this stacking between these arginines here, and you can see also the crystal mirror part of it down here too. And we've identified a bunch of residues in blue here that are within 5 angstroms but are part of our asymmetric unit as well. So maybe I was interested in designing 2 alpha helices that come together in this particular geometry, and I was looking for loops that I could model into my alpha helices, and maybe I'm looking for loops that are exposed to the solvent and therefore aren't reinforced by local interactions. And this is a way of finding out that maybe this particular loop is not a very good example of one that I could use for my design, because it seems to be very much reinforced by local interactions and by crystal interactions. And of course what you could do if you're doing some more advanced stuff is you could stick all of this into a script, and you could burn through the PDB with a script counting the amount of these different interactions in order to find loops that are interesting. How do you get data from out of PyMOL into a text file? That was another question. So you're doing all these measurements all the time, and again, if you're doing measurements and you're putting this into some form of script, then it's very useful to be able to bring those measurements out without having to jot them down on a piece of paper or start copying and pasting. This is me diverging out of PyMOL language and into some bash commands. So here I'm just going to define a chain variable called D. I'm going to define some residues, a number of residues, which is the amount of residues that are in chain D of my PDB. We don't need to go into details there. And then I'm going to, instead of writing out my PyMOL script like this, where this is directly into a PyMOL script, I can use a little function called echo, and I can use that to write out my PyMOL script for me. So what I'm going to do is fetch 3chb as usual. Then I'm going to use a bit of this is getting a little bit complicated, but a bit of Python here, because obviously PyMOL is a Python molecular viewer, and it uses Python, the Python language. And this is a bit of Python here where we can open a file that is referred to as f, called phi and psi.txt, and we can make that writable. Then we can use a few more bash loops here, make some selections of molecules, of residues. So basically we're iterating through our residue selection here. The object here, by the way, is that I'm going to make a little ramachandran plot based on the phi and psi angles of my protein. So here we're going to basically just select 3 residues, then we're going to give those residue selections particular numbers, and then inside we're going to echo into a script called phi-psi.pml, and we're going to use these commands called get dihedral. So you can actually type get dihedral straight into PyMOL here. You can see it here, get dihedral. And if you're doing a Python command, then you can, if you're doing a Python script, you can use the word command in order to script this, and then you make 4 atom selections. This is just using the standard selection nomenclature that we all know about. And then we can use some more Python here to write out our phi angle and to write out our psi angle, and then we can close the file that we had open, and then we can use PyMOL to process this PML file that we have. That all sounds quite complicated, but let's just show the example. cd temp. So what I should be able to do is just copy the whole of this. Actually, what I'll need to do first is fetch 3chb type equals pdb, and then quit, and then I should be able to do this. Okay, so what this has done is made myself a little script here based on this bit of bash here. And again, if you know any of the programming languages, you can script out how to make these scripts. So what I've essentially done is made a PML file by iterating through each of my different residues in my protein, and then and then basically calculating a dihedral for each of those. And I can, if you have a script where you've made one of these PML files and you want to run it in PyMOL, a nice little thing you can do is use the -qc command here, and that runs it basically quietly and in the background. So we can run PyMOL now in the background. Can we? There we go. Done. And what that should have done is produce this this phi_sci.txt, and then we can just use a few of the little bash commands or programming commands of your choice for whatever language you're particularly interested in, and we can convert that into something like a CSV file where we have our phi and psi angles written out from PyMOL, and we can make ourselves a little ramachandran plot. Now obviously you know, you'd want to straighten out these axes and put them to 180 in each direction, but if that's the kind of thing that's interesting for you to do, you can see that it can be quite an easy process to go through if you know your way around a little bit of coding. If you don't want to have to go through all of this kind of palaver and you're just interested in taking some stuff straight out, I've also just simplified those commands here. So all that you really need to do is, in fact, I'll make it even simpler, because here I've put in my echo commands, so we can get rid of these and these and these. And it should be similar to this here, where you open up an out file, you have some kind of command here where, like, for example, you're measuring the center of mass, or instead of center of mass here, you could replace this with distance or whatever you want, and then you have your selection within that section, and you have a variable that command and selection refers to, and then you can just simply write that out like this into that out file, and then you just close it at the end, and that writes the file for you, and that way you can save any data that you were creating. I did get a question about automated secondary structure detection. This was specifically for people who were doing molecular dynamics, because often when you do some molecular dynamics, you pass and you get your protein out of your molecular dynamic program, it loses various bits of information. And this is very, very simple. If ever you've got a problem with your secondary structure, you can just use this DSS command, and that will automatically make a detection of what the secondary structure is. And there's also a page here where it can go into details of how, if you have multi-state files, how you can use DSS to make consensuses or not have consensuses of secondary structure over different aspects of that. And often there's a command called rebuild that you need to use in order to apply those changes once you've made them. Another thing that's of interest to people is, how do I see the electron density of my model of interest? Well, obviously if you want to see the electron density, you need to download it. Now, you can either just go to these websites and download them yourself, or if you have the means of if you have again a Mac or a Linux, or if you know an appropriate Windows term, you can just download it from the command line. So for example, we have wget on Linux, and that can just be used to download those particular files straight off the internet there. And then rein. What we can do is fetch the same protein for the files that we've downloaded and load in our electron density map and our difference map. Now, of course, when you load in the maps, I mean, they don't have anything on them at the moment, because really they're a selection of of densities. So what we need to do is we need to select a particular contouring level that we want. But first what we'll do is we'll find a amino acid selection that we're interested in. We can orient around it, color it in, make everything nice and pretty, and make some sticks. So here is a protein sequence of interest that we found in the middle of our protein. Now what we can do is we've loaded up the maps, and we've got our two electron density maps here, and we can use this command called isomesh, and isomesh, we can then create a mesh with a name. So this is just the mesh name here, where this is the object, and then this is the contour factor, or the sigma level of the electron density. So that always comes out white to begin with. Oops, and then we can colour that blue. So there's our electron density map there. Then we've also got our difference map, so we can make another 2 isomeshes, one at a contour of 3 and one at -3. And then we can colour them respectively red and green. And then that gives us a difference map there as well, where we can see how well various bits of it are modelled in or not. And then again, a little bit like how we were able to trim the surface, we can also use this map trimming function, where we're going to trim everything outside of 4 angstroms. So we can do that, and that just gives us a tidier box to look at there. And then we can do some various things, like we can orient around it, make sure that we haven't got anything selected. And then if we particularly want to, we can make a very, very quick little movie, so that when we're looking at it, it can just go around, and we don't have to wiggle the mouse around as we're watching it. And what you can also do is you can stick all of this here into a script. For example, I have a little script that allows you to search for a particular structure. So for example, we can search for any PDBs that contain the word leads, and there's 6 PDBs in the PDB. Well, this is a non-redundant list. So there's a bunch of sequences here that contain that. And then what we can do is we can okay, actually that one couldn't find the leads sequence in it, so we'll quit that. But again, I'm just trying to get across that you can use these commands, integrate them with some of your scripting skills that you may have in Python or in Bash or whatever, wherever else you do your coding, and you can quite easily integrate these PyMOL scripts together in order to have a script which will carry out a particular function for you and make your life easy. So, for example, if leads was a particular sequence of interest, and for some reason I was interested in the electron density of that sequence, then this would be a very useful way of going about looking at those things. And that was the end of my question and answer session that I had scripted down, unless any of you guys have any questions on the fly. In that case, thanks again, and goodbye.